All right. Okay, so today we're going to talk about, and today next time, we're going to talk about exploratory data analysis. And exploratory data analysis really is just a catch-all term for descriptive statistics in a lot of respects. So if you're going to find out anything about a data set, you have to understand the data themselves, right? So at the beginning, you've got a big batch of numbers, big pile of numbers. You always do. And then you wonder, what am I going to do with this? Well, you have to get a good understanding of the raw data before you do any actual analysis to it, okay? So basically what I'm talking about today and next time is getting a feel for your numbers. So what do I mean by that? It's hard to put that into words, but here's some words that actually can help you, I think. It's things like I said, descriptive statistics. It's knowing where the numbers came from and where any potential problems are. And you're going to find problems, you're going to find mistakes in, say, coding. So let's say, for example, and I can think back to a study a person I know in grad school did, and he was collecting data at the Ontario Science Centre about people's smoking behavior, okay? And he was trying to predict how many cigarettes people smoke per day without using, that's easy to do, by the way, by taking a saliva sample. It's trivial. But not everybody wants to give a saliva sample. It's pretty easy to just ask people 5 or 6 questions, and if you can, what if you ask people 5 or 6 questions and they just could answer? Much better. So that's what he was trying to set up. So he would take the saliva measures, but he also asked people a whole bunch of questions and eventually built a regression model, we'll talk about that at the end of the course, predicting cigarettes per day. So one of the people he was looking at, and I have the data set because we used to use it in grad school as a thing to use for a teaching resource. And so I remember looking at this, and one person responded in the survey that they smoked 400 cigarettes a day. You can't do that. That's got to be a mistake, right? 400 a day. It's like 2 cartons of cigarettes a day. You can't smoke that much. Like you can't. It just can't be done. I've tried when I was in graduate school. You can't smoke that much. It's impossible. That's got to be a coding error, or the guy lied. It's probably 40 instead of 400. It's probably, because 40 is a little heavy smoker, but people smoke 46. Well, they used to. Does anyone know how much cigarettes cost them? I stopped smoking a long time ago.
Like $21 per cart.
Holy Christ! Really? So they're like $1 a piece. A dart's $1 a piece. Well, maybe that'll stop people from smoking more. Jesus. Yeah, you could do that now because you have to be wealthy beyond the dreams of avarice to smoke 400 cigarettes a day. Yeah, so that's got to be a mistake. And if you're looking through your numbers without doing any analysis, just looking through going, wait a second, triple digits, that's a problem. You can actually maybe guess what actually happened. One of the things that we're going to see here is that we're talking about doing things like, scatter plots and histograms, really simple things you were taught in the early days of 2126, but they're super useful. So if we look at something, for example, again, let's think of the cigarettes example I was just talking about, and we had a distribution of, like a histogram of how many cigarettes people smoked a day, maybe we saw something like that. We'd go, oh, okay, so there's some people smoke a little bit, and there's some people smoke a lot. A little bit more than that. This gives us an idea that we should expect something like that. We might look at that and go, maybe we have 2 separate populations. Maybe when we're trying to understand cigarette smoking behavior, we should think of heavy smokers and not so heavy smokers, right? And that's just by looking at a histogram. And I said odd values as well, the idea of someone smoking 400 cigarettes a day. There was another one in there where a guy said he started smoking at 3 years old. There are people like that in the world. It's possible. Every so often there's a viral baby smoking on YouTube, which is both funny and gross. But it's possible. Probably not, but it's possible. So you look it up and you find out, you go back. Maybe you throw those data out. That's what you typically do with stuff like that. Because like the 400 a day, you don't know if that's a typo or that's a lie or something. So you know what you do? Throw out their data. You can't use those data. If you could go back and find a guy and say, and you see him and he's just covered in yellow nicotine stains and he's shaking, go, yeah, you probably do smoke 400 cigarettes a day. Most people don't. So that's kind of why we're doing this, is to get a feel, like I said, get a feel for your numbers. So it's, like I said, this is one of the most important and really overlooked areas of statistics. It's called exploratory data analysis. And this is, I've developed, probably this is the wrong way to put this, because these techniques have been around since, well, before all the inferential techniques we'll talk about in this course. But this was all put together in a book called Exploratory Data Analysis by a guy named John Tukey. You may have heard of Tukey. The Tukey test, which is a post hoc test analysis of variance. This allows you to generate hypotheses as well, and just get a feel for your numbers. This is something that, for me, one of the first things I do with my honor students when they get their data and they come and talk about their data, I say, let's look at some charts. Let's look at some graphs. Let's just look, what are averages? Don't do any analyses yet. Let's just tell me let's get a feel for them, right? This also gives you an idea of how the experiment went without losing any of the richness of your data. Like if you see something like, oh, I got two groups, and it doesn't matter, but you got two groups, you just draw a bar graph and you go, oh, something happened. Like, I mean, if you see that, you should say, if my inferential techniques don't pick this up, there's something wrong with my inferential techniques. It's not that there's something wrong with the data necessarily. So you might look at that and say, oh, something probably happened. Let's see if we can find it. My PhD advisor used to say that statistics are there to prove what you already know. You should be able to look at a data set and go, I think I know what happened. Now let's make sure this isn't due simply to random chance, random variation. Okay? All right. Questions so far? Yeah? You good? All right. Say, I don't know what these numbers are. They're numbers. I have no creativity whatsoever, so making up examples is not great. Let's pretend. Let's pretend that there was a test in this course out of 35. It's not. The first test is out of 60, and the second one's out of 40. Well, at least last year it was. Maybe it'll be different. 65, maybe? That doesn't matter. This is just what's called a relative frequency table. Okay, so this actually, we have all the numbers here, all the data values. And we have how many, right? One person got 10 out of 35. That's not very good. They may not have been in the right class. You ever do that? You ever go to the wrong class? I did that first year. I went to a wrong class. It was a fourth year chemistry class. You just sat there. Because I was so embarrassed. I mean, I shouldn't have been embarrassed. It would have just been no big deal. But it was like my second day of university. And I'm like, oh, I'm scared. I don't think I'm taking chemistry. I'm certainly not taking a fourth year one. The course starts with a 4. It's supposed to be in political science. Anyway. And it turned out I wasn't even supposed to be in anything at that point. I completely misread my schedule. University. So maybe that was me. Hey, somebody got perfect. That's good. Most people around here, that's what you'd expect, probably. But you might look at that and say, somebody got 10 out of 35, like 23. Look at the rest of them are pretty reasonable. Then that person, so you might look at that and go, okay, what's going on there? What's going on there? That person missed a lot of class. Are they just confused? That's also possible. Believe me. Believe me. But could be there's the wrong class. Two different populations, who knows? But the nice thing about this is it gives you, all the numbers are still here, but we don't just see 10, 23, 23, 25, 25, 25, 25, 25, 30, 33, 35. 30. I missed one of the 30s. We don't see that. We actually see, this is just a summary. It'll help us. So that's one thing to start with. The nice thing about a frequency table is it makes some things easy. You can actually get the sum of the x's, that's all the values, times their frequencies, will give you the total value of all the scores, right? In our case here, it's 309. This is 35, a 33, two 30s, 5 25s, 2 23s, and then, of course, our friend who got 10. Now, why is that useful? Well, obviously, we're going to use that to calculate means, etc., right? So that's going to be extremely useful, right? Okay. So we can even put that together into a relative frequency histogram. Looks like that. How did I do that? I can't remember. Oh, I know what I did. I just put all the numbers into a spreadsheet program and said histogram. I selected histogram. I think it was the Apple numbers program. remember, when you're doing stuff like this, you're not doing it for publication or presentation purposes. You're doing this to look at your numbers. So what this is doing, and when you think about it, it really is just a graphical representation of exactly what is in the table it should be, right? Now, the scale's awful. There's no there's no quarter of a thing, but who cares? That's not why if we were using this for publication or for presentation purposes, we'd fix that. We'd make the scale 1, 2, 3, 4, 5. Right? Because it's cleaner. It makes more sense. A quarter doesn't make any sense but it just did that. And I don't care because I'm not presenting this anywhere. I'm doing this for myself. And I'm looking at this going, what's going on here? This really gives you a feel for, that's very far from the rest of the distribution. So that's the big difference here. You might think, well, this is doing the same thing the relative frequency table's doing. Yeah. It is, but it's also giving us a sort of pictorial view of how far away this one observation is from the rest of them. Like, these ones here are these are amazing marks, but they don't seem ridiculous if that was the whole class. If we throw in this one at the end, then it's weird that that's there, right? And I'm not saying I don't see, I do see things like that, but I can tell you that when I do analyze, and I do analyze the data of all my classes to make sure everything's cool. And last year, for example, last term in 2606, some people failed that class. And I thought, well, that's weird, way more than normal. So I threw it into SPSS, and I told it to make a histogram, and I went, oh, I see what happened. Because I had this. I literally had this, except it was like this. There's a bunch here, and then nothing, and then the regular. These are the people who never came to class. That's what it was. I didn't know that for sure, but I could look and go, I don't know your name, I don't know you, I don't know you. So it's easy to figure out, oh, they didn't come. And as I think most of you know, who have had me, I think, involved, not coming to class is a really good way to fail a class of mine. Or anybody else's. I don't get not coming to class. But anyway, it's your money, and you're all here. That's good. We've lost no richness in the data. We could actually completely, by looking at this, build the data set again, easily. Right? We can reconstruct it. No problem. We've lost nothing. We've lost nothing in the fidelity. It's a simple, I'm not going to use those words, forget it. It's just, sometimes I edit things out on the way. Okay, I'll say it. In we call that a functioning isomorphism. You can actually do a very quick transformation to this and get back to the original. Okay, that's all that's saying. Okay. We can spot outliers again. That one's weird. And I would be concerned. Like I said, when I looked at my marks for 2606 last term, I was like, what's going on? And when I took those out, those like 18 people who got like 6 in a class and took all the tests, it seems to me that after you get 6 out of 60 on your first test, you think, probably should start studying. But you think, no, I'm going to keep going like this. So you get 4 out of 50 on your second test. You think, you know what? No, everything's going perfect. I'm going to not study for the final. I don't understand people. Anyway, when I took those out and I just looked at these data, it's like, oh, it looks completely exactly the way it should. The average is 66, which is the average in that course always. I've taught the course 31 times. It's like always between 64 and 67, just where it lives. So I was like, oh, good. Now I know what happened. It's not that I've completely snapped and become horrible at this job. Maybe it is. Don't tell anybody. It's because a bunch of people stopped caring, so cool. And as I've often said to you, I can't care more than they do. Right. What about categorical data? Those are numbers. Numbers are easy. Categorical things are a little harder. We don't get a histogram, we get a bar graph. It serves a similar purpose. It's just that the categories aren't numerical. You do pie charts too. I don't get pie charts. If you like pie charts, you're doing exploratory data analysis, you should do pie charts. They're for you. So the x-axis doesn't have any meaning in a relative frequency histogram. sorry, in a bar graph compared to a relative frequency histogram, because a histogram actually, the x-axis, the values have meaning. The values have meaning with categorical data too, except that if it's hair color, we don't go brown, red, blonde, whatever, and then say, oh, blonde's more hair colory than brown. What does it even mean? Like, the scale doesn't mean anything, you know what I mean? So let's say we had a STAT 2126 class, right? And it was a time when we taught all the people stats, psychology. It was a fascinating time. Let's say you got a class like this, and we got 38 psychology majors, 15 sociology, 18 CEs. I don't know, 5 biology majors. You can see that I made this example up a long time ago. This does not reflect the, we'll probably go like, they would be up here with us, if you were them. One of the nice things about teaching this stuff is you can make up slides 20 years ago, and it doesn't change that much, because you know what? The way you take an average hasn't changed. The way you do analysis of variance, pretty much the same. So, one of the upsides of teaching this stuff. Anyway, so that's some things. In fact, and this is actually from the STAT 2126 class that I had, mid 2000s, like mid aughts, so probably around 2006 or something like that. So it would look like that. Now, again, I just threw this into, I'm pretty sure that's Mac OS numbers, and I said, here, make me a graph. Okay, psychology, sociology, CESD. Is sociology being to the right of psychology, does that matter? Doesn't make any difference. Those differences between the spaces don't mean anything. Like, is the difference between psychology and sociology the same as the difference between biology and, what does that even mean? Like that, you can't, so the scale means nothing in these. I could have made this so this was over here, and this one was here, and that one was there. Like, who cares? It doesn't matter. Yes? Doesn't matter at all. So you can do this any way you want. And again, you typically, maybe you might use this, something like that for presentation, I'm not sure. But mostly at this point, you're doing this for yourself. You're doing this because you want to know what's going on. Oh, here is a pie chart. I don't know. I thought, why not? There's a pie chart. This makes a lot, now I don't know about you guys. So, and again, you're doing this for yourself. So if this makes more sense to you than this, then when you're doing this for yourself, like for your honors thesis experiments and stuff, when you eventually get there, do that. I mean, that's, to me, whenever I see this, I think, well, if we're looking at the first quarter earnings, then I throw up my mouth a little bit. But if you like that, do it. It's not bad. I've never, in what I do, no one does this, so I have no experience looking at pie charts. Just none. So why would I start? Okay. All right, questions so far? Yeah, good. All right. So quantitative variables, of course, with those we use a histogram, as I mentioned. So the nice thing about quantitative variables is we can actually put numbers on things because they're quantities. So we can describe batches of numbers with other numbers. Right? So if I said to you, what's the average hair color? You'd go, I'm sorry, that's a stupid question. What's the standard deviation of hair color? That's a stupid question. You can't use those things to describe that. But if I said, what's the standard deviation of the heights of the students in the class? Well, you all know what that means. Right? So quantitative variables are really nice, and we kind of strive to use those if we can. Just because you can do math on quantitative things. You can't do math on hair color. We can look at central tendency then, you can look at spread, just how spread out something is, and I just mentioned standard deviation. That's just one spread measure. Just thought of 4 others. Like, there's a lot of others. The one we tend to use is variance and standard deviation. We can see the shape of a distribution. So remember I said the shape of the distribution of my intro to neuroscience class last term, I looked at it and went, that looks wrong. There's a bump over here that isn't supposed to be there. And I can tell you that very often, the shape of the distribution in, especially STAT 2126, but very often in this course too, at the beginning, not at the end. At the beginning, though, this course, the distribution kind of looks like this. Something like that. This might be higher, this might be higher. It's bimodal. It's got two modes, basically. And one's a little higher, doesn't matter. It almost always looks like that. 21, 26 looks way more like that. It looks like that at the end. This doesn't look like that at the end. Right. Does it bother anybody, or you're okay? This is bothering you, I'll tell them to shut up, but if it's not bothering you, it's fine. Okay, cool. Because I'm not closing the door. It gets too stuffy, and also there's always an off chance of getting more COVID. And I've had it once, thanks. And that's enough. That's enough. So central tendency, shape, spread. Those are important things. We get to see those with quantitative variables. So how can we describe shape? Let's start there. We can talk about skewness. A negative skew, this is weird always to me, and it may be to you. The negative skew means most of the stuff is to the right. The positive skew is most of the stuff to the left. Now the way, if you think, I'm never going to remember that, well, there's two ways. One way is you can think, the way that seems to make sense is wrong. The other way is you can say, the tail tells the tale. I feel gross just saying that, but it's true. Positive, negative, the tail tells the tale. I don't like little sayings like that for some reason. I think it's childish. However, that's how I still remember it. So, just, you know what? You know how I still to this day remember that inequality signs. So like the alligator's mouth always points to the biggest piece of food. I still remember it that way because I was taught that in grade 2. One thing Miss Byers taught me. Bitch. She took my hockey cards. She took my hockey cards. Don't take my hockey cards. Really, you trade hockey cards. And I had lots, because actually I wasn't collecting hockey cards, my dad was collecting hockey cards. And I was like, it's ages. I mean, he was going, I bought more cards, Dave. But Daddy, I've got a million of them. So I traded them. But I'd never tried, I was very rule-bound as a child. Which I maybe find hard to believe, but I wasn't. I would trade it in class only before or at recess. Teacher takes them from me. And the neat thing was that night, it was parent-teacher night. It was like a movie. And it was 1972. Dads didn't go to parent-teacher night in 1972. But this time Dad went. And just, I stood outside the classroom. Because they had a part where you didn't have the kid there, you're talking about the kids more, and then, you know. So I'm standing outside the classroom like this. And I'm hearing my dad say, are you giving my son his property back, or are we calling the police? And I'm sitting there going, this is the greatest moment of my life, and I'm 7. It's all downhill from here. So she gives me the cards back, and I come in, and Dad gives me the cards, and he says, now, David, remember, when you bring your hockey cards to school, always leave them in a big pile on your desk so your teacher knows you're not trading them during class. And I thought, yes, Daddy. And of course, what my dad was doing was saying, fuck you, lady, he's going to bring them every day, and you're going to see them. Which I thought, God, I miss my father. I don't, skewness, we can talk about skewness. There are numbers that we can use that describe skewness. I don't know how they work, and I don't care. To me, it's more a descriptive thing. I can look at that and go, they're skewed to the left, skewed to the right, or negative skew, positive skew. We expect, this is in fact what typically happens to the distribution in this class. At the end of the course, it's way skewed over there. It's negative skew. It just works like that. People tend to do well. And there's a couple that don't, but typically it'll be okay. Okay. You could describe kurtosis, which sounds like something they treat outpatient, but, and you know what? I'd never know this until I see this slide and go, leptokurtic means peaked. Leptokurtic, and then platykurtic means flat. Back before Paul lost all that weight, I used to say that I was leptokurtic and he was platykurtic, but I can't say that anymore. It's no fun. I can't make fun fun of him being, a fat bastard anymore, because he's not. I got a thing once in my professor teacher, like the student evaluation of teaching, that said I was unprofessional for making fun of my colleagues. Bite me. I only make fun of people I like. Don't try to do that and go, he's never made fun of this person, he must hate them. It doesn't work like that. Again, I don't know these terms, but I know what kurtosis means. It's how peak the distribution is. But the pletokurtic and lactic, you don't have to know that. It's something you might run into. And again, there are numbers that, when SPSS gives you descriptive statistics, you will get kurtosis numbers. I don't know how to interpret them. And it doesn't matter for our purposes. I'm just talking about this now because it's just another way to describe shape. And we can quantify this. It's not a big deal for our purposes. Distribution can also be symmetrical or asymmetrical. Of course. Right? Could be worse, could be drill bits. That was really something. Right? This I just found fun, so I'm going to do it. I also love watching the person drive by on wood polisher. I kind of want to do it. I asked what's that fun, and the person said, the first time for about 10 minutes. And after that, it's just work. Distribution can be unimodal or bimodal. These are bimodal. If we just cut that off, it's unimodal, one mode. I'm not surprised it needs a jet engine. But so a lot of classes you'll see bimodal distribution. It's very common. First year you teach intro psych, which I don't do anymore because I think the department stopped me from teaching intro because I think I scare away the kids. But it's like, it used to be when I was younger. It's like, oh look, they're all cool and young and hip. When I was like 35 or 30, 28. Oh, look, Dave can teach you. He'll bring him in. And then it's like, don't get the old guy who's got a bad attitude to teach them. He'll destroy them. Anyway, but when you teach intro, it's great. It's always bimodal. Always. Doesn't matter what you do. You can do everything. Because there's people who get into university in first year who should be here, right? It should be easy to get in. I'm all for that. It should be easy to get rid of you. It's not even good to work. And a lot of those people that are over here end up either not coming back or being asked not to come back. But you always see a bimodal distribution. And in fact, when you don't, you'd be surprised teaching an intro level class. You'd be very surprised not to see a bimodal distribution. And that's not a thing about only recently or whatever. That's always been like that. It could be a uniform distribution. It could be all scores have the equal possibility of showing up. So we could have a uniform distribution. Here's an example. So I just picked this. I came up with some numbers. Well, I didn't come up with them. I thought I'd get some real numbers. Those of you who don't follow hockey, and now at this point, this is basically hockey history in a lot of respects, may not know about Mario Lemieux. There he is in 2002, carrying our flag when we won the gold medal in men's ice hockey. And that's the first time we won a gold medal since 1956 because he hadn't sent good players. Used to be you could send all of us over to Europe to win the world championship and we beat them. Or at least we competitive. Mario was an amazing man. He played from 84 until about 99. Then he retired because he had non-Hodgkin's lymphoma. So he had, oh, by the way, yeah, that's right, sorry. 1 year he was out for 6 weeks on the disabled list with cancer. He came back and won the scoring title. He missed 25 games. Still won the scoring title. Eventually his back got screwed up so much that he quit. And then the team still owed him all kinds of money. And they couldn't pay it. So he said, fine, give me the team. So he now owns the team. And then, he's like, a couple years after, he goes, I'm going to start playing again. So he plays again. He's the owner of the team he's playing for. The best part was when he'd turn around and look at the coach and be like, I could fire you. But she didn't do that. But he was an incredible hockey player. I contend he's the greatest hockey player of all time. Here's some goal totals. By the way, 50 is an impressive thing in hockey, okay? So here's some of his goal totals. That's his first year. He's 18 years old there. Oh, that's a high one. Oh, that's another high one. And then there's always these weird ones, like 30, 17, 6. He got hurt a lot. He had a bad back throughout his career. And like I said, he was also out a year with cancer. Those are some pretty impressive numbers. Those aren't... He came back and played until, I think, 2006 is the last year he played. Anyway. So a histogram is probably a start, but I think you probably want to group the values. So we're going to try to get an idea about Mario Lemieux's scoring, goal scoring, by looking at a distribution of his scores, of goal totals for each season. We could do a histogram, but we just have one at each, 43, 48, 54, 70. That's not going to help us. Do we have anything that's repeated? No, they're all different, aren't they? Yeah, they're all different. So we just have little bars, but we have to group them. So, again, I just told a piece of software making a histogram. I didn't tell it what the interval should be. I had it pick them. So basically what this is 65 to 75, 85, or 75 to 85, 85 to 95. That's why that one is there at 90, because he did score 85 goals one year, and the limit is 85 to 95. Or 85 to 94, rather. This gives you an idea here of, he's had some great years, but also he's got quite a few years here where he's got, very few goals. Right? So that 90 is because the limits go from 85 to 94. So the limits of the category. That's one of those things. You still worry about that in 21-26 about real limits on graphs? No? Does Dwayne still make you do that? I think it's fine that he does. I'm just curious. Because I usually skip it.
You have the same example.
Oh, I know. He told these are my slides. I gave them to him. Well, no. We all do that when we start. When the new person starts and they take a course, you say, "What do you need?" Right? Is anybody taking 4007 right now? No. Okay. Good. Like Dr. Pastore just took that course and she just started, and I'm sure either Dwayne or Paul gave her his stuff for history of psych, or it contemporary theory. We all do that. Yeah. So the reason you've seen this slide before is because I gave Dwayne my slide. Dwayne took this class from me at Monday. So he's not only taught from these slides, he's been taught these slides. All right. So the real limits, don't worry about real limits. It's not something to get too concerned about. Frankly, software takes care of stuff for us now, so we don't have to draw our own graphs. We used to have to worry more about that when we draw our own graphs. Basically, no one draws their own graphs anymore. I will say there is something to be said for if you have too much data, doing things by hand. You really get a feel for stuff when you do it by hand. Any arithmetic or, quick stuff with graphs. Now, if you can, there's nothing. It's good, in fact. And I've had entire honors thesis projects that we've analyzed by hand. Because you can. Sometimes you can. I was talking to an old former student of ours who's now a PhD student. We were talking about it yesterday. She wanted some stats advice. And we were going through things, and I said, okay, that one you can just do that thing by hand. Don't even take the time to put it in SPSS. It'll take longer than getting out a calculator. Right? So there are times you can do stuff by hand too. And like I said, I'd probably draw these graphs by hand. Piece of graph paper, feel like you're in grade 4 again. So the scale has to make sense. Again, this is only for you, really. That's what you do while you're doing exploratory data analysis. But sometimes stuff shows up in exploratory data analysis and you've got a histogram or something, you might want to use it for presentation purposes. Like, think about the y-axis of a graph. And we've got something like, so let's just, okay, so, got three categories here. We'll go with electric and oil and gas. These are different ways to heat your, oh, and wood, useful. Ways to heat your house and how much it costs every month. Okay? This is an actual thing I've seen. Okay, that's why I'm showing this. Okay, so let's say electric's more expensive. And I've seen this actual thing given to me by Newfoundland Light and Power, back when I was, because they were trying to get you to use electric heat, which is an interesting choice, rather than oil. A lot of people in Newfoundland use oil, or wood. And a small number use propane. There's no natural gas in Newfoundland. So you get this and you think, God, I shouldn't have electric. It's ridiculous. Look at how high it is. But then when you look at the scale, and this was how much it will cost you per month, was like, by the way, remember this is 25 years ago when I saw this. It's like 80. Suddenly, oh, it's $8 more a month. It's not 5 times as much. Now, were they trying to lie to me? Well, yeah, of course they were. They were trying to get me to use oil. By the way, strangely enough, I already was using oil heat. So I don't even know why I got the mailer. But you can see something like this where this scale is meaningless. Starting at 80 and just going up to 90 doesn't matter. So you have to, especially when you just throw things into software and just say, show me something, you've got to be careful. Just look at the axis, make sure the axis scale is sensible. This is something you will see, by the way, in political campaigns, which will likely have an election probably in April. I would assume maybe May. You'll see all the political parties do things like this. It's bizarre. You'll probably see, and it depends on the year, usually one sort of team picks up on more than another. But the use of, see, this isn't a lie. It's just shitty. They're not lying to you, these are all real numbers. And I mean, when I got that thing from Newfoundland Light and Power, it was from the oil. That's right, it was Irving Oil, because that wouldn't make any sense. And it had a source for the data, like it told me where it came from, it's just the graph is shitty. So yeah, you'll see it during political campaigns, for sure. Outside must be, yeah, I am. So one of the problems with a histogram, like we had with Mario Lemieux's goal scoring, is group data like that, you'll lose some of the richness of the data. That's okay with a big data set. I talked about this stuff about smoking. We had 500, or my friend, I shouldn't call him a friend. It's a long story. Anyway, the person I know, he had 500 records there. It's a lot of data. You don't really need to worry about losing richness in that. But we only had, 12, 15 years there. Do we really want to lose that richness? So it's something to consider. It's something to consider. Like when you have 500 records, you kind of want to get rid of some of the richness, right? Because it's hard to just look at a batch of 500 numbers and feel something, and get a feel for it. You can look at a batch of 20 numbers if you've looked at numbers enough in your life and go, I see what's happening, right? My PhD advisor could do calculus in her head, but couldn't do like a t-test. And she was always amazed that there's a thing that I could do, which with a batch of about 20 numbers, I can look at it and tell you what the mean is and standard deviation. Within reason. It's not dead on, I'm not Rain Man. 247, yeah. But it's something I can do because I play with numbers a lot. Not that impressive. A lot of people can do that. But the thing is, beyond about 20 numbers, I just can't do that. About 20 I can look, about there, Oh, here's something you can do. You have a stem and leaf plot, which is, what a stupid name. What a stupid name. Anyway, there's a stem and leaf plot. This is an ordered stem and leaf plot. See the order. Now, how does this work? the stem, like, why did somebody this has got to be somebody invented this and went to their like child and said, what should I call this? Like, you make it sound really stupid, so people will be embarrassed to say it in public. So these are those goal totals. So there's 1, 6, 7, 17, 19, 28, 35, 43, 44, 45, 48, etc. Now, assuming I've copied those numbers that, transposed them correctly, and I don't know if I have. I made a mistake. I don't know. But the important thing is that I think you can see that this gives you all the numbers, and it gives you the shape of the distribution. You just got to turn your head on its side and go, oh yeah, I see. It's really nice. I have seen one of these in a presentation once in my whole life. My whole career, I one day saw a standard leaf plot. Because that's not what they're for. They're for me, like me being the researcher. They're for me just looking at my data. They're not there for any other purpose. You're not going to put this in a paper or a talk or something. Like I said, I've seen it once. It's called an ordered stem and leaf plot because it was 43, 44, 45, 48. You could do an unordered one. I don't know why. What extra work is it to order it? But you can do an unordered one. If, what it is, it's probably some guy started doing it. And they're like, you can put them not in order, and then that's my invention. Yep.
Yes, so I'm just confused a little bit. Is the first column the frequency?
No, this is the tens, this is the ones. 17, 19, 28, 35, 43, 44, 45, 48. Does it make sense?
No.
Okay. So if we have the number, so I can reconstruct this. I'll show you how to reconstruct the data from the stem and leaf plot. Let's look at it. So here's the goals. 1, is that 6, 7, 17, 19, 28, 5, 85. So it's a way of ordering the data set, and you have all the numbers, but also the weird thing it allows you to do is you sort of turn your head, you still can see the shape of the distribution. So it's not frequencies, these are the actual numbers. That's the tens column, that's the ones column.
These are all values?
Yeah.
Okay.
Exactly. So that's going back a couple slides to the goal totals from our other ones. Okay. Yep. And again, assuming I copied those numbers properly. There may be a mistake. Hopefully you can see that the point of this, not that I made a mistake. I'm not even sure I did make a mistake. I'm just saying it's possible I did. Other questions about stem plots? Okay. You interpret this just like a histogram. It basically is one when you turn your head on its side, right? So it's easy to spot outliers or to just spot them. Yeah, you can look at this and go, outlier isn't quite the right word, but what's going on here? And then, as I told you, he had an injury-plagued career. And then you go, okay. So a lot of times when he just didn't play too much, and he got hurt. Yeah. By the way, the year that he was out for 6 weeks with cancer, he scored 70 goals. I'm out with a little cancer. He's got a little touch of cancer. I'll be fine. As a Superman. Preserves all the data. All the data are still there. All those goal totals are still there. Right? It's easy to get the middle or the 50th percentile. Percentile just is the 50th percentile means you're at the place where 50% of the people are below and above you, Like the 60th percentile is we're at 60, we're at 70, etc. Halfway is going to be 50. Well, let's see, how many values are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So that means the 9th value is the middle. Right? Because 8 and 8 is 16, there'll be 8 here, and then 1 in the middle. Let's go. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, look, it's 44. I want it right. That's the median, or the 50th percentile. It's the middle. That's the middle, or the median, or the 50th percentile. And yeah, are there formulas you can use to count? Yeah, sure. There's also, you can just count under your finger. I think our book actually has a formula. There is a formula you can use. Why? I don't get why you'd use a formula when you can just count like this. All right. So do you see what I've done here? Basically just a standard stem and leaf plot, and I just count it. Where's the middle? Where's the middle value? Okay. Oh, the whole thing came up. Okay, what you can get from this, from a stem and leaf plot, is something called a 5-number summary. A 5-number summary is a great way to just very roughly summarize a batch of numbers. You get the median. That's the middle. The median is the middle, 50th percentile. Pulled something in my shoulder shoveling the driveway before I had to leave yesterday, and it's very hard to do things. I'm old. Oh, the quartiles are the medians of the first half and the second half. That's all it is. So it's 19. Let me just go back. I'll come back to this. Don't I'll go. One of my least favorite things in the world is a whole class gasping because I've moved a slide. Okay. All right. So let's see if we can do this. See if I did it right. So if that's the median, right? So we know the first half goes, let's see, 1, 2, 3, 4, 5, 6, 7, 8. There's 9 numbers in the first half. So what's that mean? That means there's going to be 4 on one side, 4 on the other, and 1 in the middle. So it's the 5th number. 1, 2, 3, 4. Thank God I did it right. Okay, so the second one's going to be the same. So we're going to go from here. 1, 2, 3, 4, 5. So it should be 54. Is that what I have on the slide? Yes. Good, I did it right. I must have corrected this because at some point in my life, I think there was a bunch of mechanical errors here. Which we all make now and then. So the quartiles are the 25th and 75th percentile. So now you've got the 25th, 75th, or 75th, yeah, 75th, 25th, 50th, median. You've also, well, there's going to be 2 more numbers, obviously, in the 5-number summary. Minimum and maximum. I get distracted by shiny objects sometimes, sorry. My brother just got diagnosed with ADHD. He's 57. I kind of wonder if I have it. Thing is, I've only got about 7 more years doing this job. Who cares? I'm basically phoning it in at this point. Kidding. These are jokes. I care deeply about all of you. And I care about your success and blah, 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 blah. I really do want you to do well. But if you don't, it really is actually, I want you to do well. Okay. You said there were 5 numbers, yes. There are 5 numbers. Star Trek, there are 5 lights. Shady Command, part 2, come on. Star Trek Next Generation, nobody watches, come on, you must have, nobody? Bunch of losers. Okay, maybe I'm the loser for quoting Star Trek. That's a possibility. Let's completely reject that out of hand. Okay, so there's a minimum and a maximum. That's good. That gives you your 5-number summary. You might say, Dave, why are we doing this? And well, first of all, I've got to fill up some time. But secondly, nothing. But secondly, this allows you, the 5-number summary actually allows you to build a thing that has an even more cutesy name than a stem and leaf plot. It allows you to build a box and whisker plot. Again, I imagine, invented by the same person's child. That's I'm just guessing, but this will give you an idea of the shape of the data. Or a box plot. Box plot sounds a little more adult to me. It's a box and whisker plot. It's cool. New from Kinner. But this will give you an idea of the shape, and I'll show you one in a second. There's also, I've posted a video on the LMS of how to do a box plot in SPSS. Because you have to do a box plot for the first assignment. So you probably want to watch that video. I think it's actually PSBB. It's one of the two. And I show you how to do it. Like I literally show you how to do part of the assignment. I actually show you the thing. So you could be able to do it. Okay. Here's a box plot. Isn't that pretty? This is a box. And these are the whiskers. It's a box and whisker plot. So, what do we have here? 50th percentile, 25th percentile, 75th percentile, maximum, minimum. Now, there's a couple of ways you can make this. One of them is you can go all the way to the ends to do what are called the whiskers. The other way to do it, and that's what's happening here. Because basically, that's at 1, and that's at 95, or 85, right? That makes sense here because you can't get fewer than 0 goals in a year. And as hard as the Toronto Maple Leafs try every year. But, so you would go, well, it'd be stupid to have it go below. But typically what you would do, so this is a special case. What you typically do is, in fact, look at this distance from the 25th to the 75th percentile. That's called the interquartile distance, or the interquartile range. It's either. And then what you do is you do 1.5 interquartile distances from the median to the top whisker, and the same to the bottom. And that's not what this is, as you can see. What we've done here is just gone to the minimum and the maximum, which makes more sense because if you did that, you actually go down below here. That's what this little mark is showing. That SPSS just did that for me. So I just threw that in the SPSS and said, do this, and it did. That's all that is. I think it's unlimited DSP. You don't see these very often in presentations or in papers, but you do. You might now and then. This actually gives, look at, there must be much more data bunched up in here than there is in here. Like this gives you an idea of shape once you have to read these things. Right? I have seen these at talks. I used to say, you never see these in a professional presentation thing, they're always done for you. And I was at a conference about 6 years ago, and the same conference I'm going to go to in March at the end there. And I saw it right away. I took a picture and posted it and sent it to the whole class. Like, no, I was wrong. Sometimes people use them, but that's like, I've seen it I think twice in my career. But it does happen, and because it can be useful. Again, typically this is just for your own use, right? Let's continue on. We talked about the central tendency of the distribution. This is one of the 3 properties, right? Shape, spread, central tendency. So we can talk about central tendency, shape, and spread. Those are our 3 things that we can use to describe a distribution typically. All right. All right, here's an example. So consider some numbers. Even more, I don't know what these are. What these are just some numbers. 1, 5, 9, 20, 30, and the numbers 11, 12, 13, 14, 15. Both of these have the same mean. I didn't go over how to calculate a mean. I'm working under the assumption you can all do that. The mean's 35. Or sorry, 13, 35. So 65 is the total divided by the 5 numbers. You get 13 for both. Both have the same mean. batches of numbers. They're very different batches of numbers. They just have the same meaning. So if we look at these again, they both have the same mean, and they're both symmetrical too. They're just uniform, right? They're just points. So those two things, we say they're both symmetrical, they're both uniform, and they both have a mean of 13. And you start thinking, well, are they the same? And they're not the same. You can look at that. God, my shoulder hurts. Let's try using the left arm. I'm just not used to using my left arm like that. But how are they different? Well, they're obviously, one's a hell of a lot more spread out than the other one, right? One's a lot more spread out than the other one. Okay. So what we're going to need is some numerical description of spread. We have to have, we wouldn't necessarily need it, but if we're going to do things with numbers, we need numbers. So we're going to have to describe the spread using numbers. Oh, we can do that. The range is a start. It's not much of a start, but it's the crudest measure of spread outedness, but it's still a measure, right? So for example, if I look at a class and I saw a distribution that looked like this, but the minimum was 70 and the maximum was 95, I'd go, well, fine. Some people got these, and a lot of people did really, 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 really well. I would probably be a little concerned about that too, but just describing the spread outedness with words is going to help us. I need some numbers here. But the range in that case would probably be useful. 70 to 95 versus, 0 to 100. Well, with our example we had here, 1 to 30 versus 11 to 15. Sometimes you'll see that written 1 to 30. Sometimes you'll see that called 29 and 4. I don't think that's as useful. Just giving a range number, I think the minimum and maximum actually really helps you. So using those two numbers. It's pretty crude, but it tells you something. Tells you something. I haven't done this in front of people. Like I've done it online, this course, for the last 2 years. It's so much more fun doing this like this. It's easier doing it online. Once a week, I fire up my computer and go, anybody have any questions? But this is much more fun. So it seems pretty crude, because it is. We can look at the interquartile distance. That's the distance between the 25th and the 75th percentile, the interquartile distance or the interquartile range. That's a little more, that's going to tell us how big the major part, like the box part of the distribution is. It's still pretty crude, but it's a bit better than the range, I think. Because that tells us where most of the numbers are. The range tells us where all of the numbers are. The IQD is going to tell us where most of the numbers are. That's a bit better. It's not perfect, but it's a bit better. We need something better, though. Something that we kind of like the mean. What we need is a number that describes spread outedness. Right? Like you get what a mean is. Right? Like we all know what a mean is. We need something like a mean, but for how spread out a data set is. Sort of like the average amount data are spread out. And I remember when we talked about, I remember learning this stuff and by the way, as you probably guess, we're really doing all of 21, 26 in the next 3 weeks, just to get you all back where you were. I remember learning about this in my intro stats class in 1985 and thinking, well, just take the average and how far the numbers are. That makes sense. It's intuitively very pleasing. So let's try that. Okay, sure. So here's our numbers. So this is the sum of the numbers minus the mean divided by the number of numbers. 1 minus 13 plus 5 minus 13 plus 9 minus 13, blah, 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 over 5. Problem is, it's 0. Is there no spread outedness in that batch of numbers? Well, no, there's certainly spread outedness, but it ends up being 0. This clearly is not going to be a very useful quantity, and in fact, if you look at that mathematically, what's the mean? It's a balancing point. right? So there should be just as much on either side. It should always, even if you can't see that mathematically, that will always be 0. Like, so even if that doesn't intuitively make sense to you, that will always be 0. Think about what the mean is. It's a balancing point. That means there must be just as much on either side. It's always going to be 0. Right? Oh, well, that seemed like a good idea at the time. This is always going to sum to 0. Like, the mean is a balancing point. I guess I should have come up with that slide before I said all the things I just said. As you probably guessed, I said these things all before. All of this has happened before, and all of it will happen again. So, how do we get rid of negatives? Well, remember in school when you learned about absolute value and you thought to yourself, I'm never ever in my life going to use this. You are about to. Woohoo! By the way, spoiler alert, it's still useless, but at least you're about to use absolute value. It's going to be useless for our purposes. You use absolute value all the time, you just not where you're doing it. Remember before when I said you'd have 4 on one side, 4 on the other? Well, that's plus 4 and minus 4, except we don't use the signs. We use absolute value constantly. But formally, we're going to use absolute value here. We take the absolute value of that expression, right? So the sum of the absolute value of x minus x bar. We're going to get rid of the signs. Hey, we get a number that isn't 0. I'm very excited. So just taking the signs away. So 24 plus 7, 31, 48, divided by 5, not plus 6. That's a number. Cool, that's great. We've solved the problem. Except we haven't. So, this is called the mean absolute deviation, or MAD. It's a great name. It has a use in statistics, not the kind of statistics we're going to do in here. And not the kind of statistics typically that we would do generally. It comes up, you will see it, now you know what it is, and you could work with it if you had to, but I would avoid it like the plague. It's kind of a dead end. It's used in what's called non-parametric statistics. The stats we're doing in here allows us to, and we'll talk about this as the course goes along, to generalize from samples to populations. Non-parametric statistics, where this is useful, allow you to say, that's what happened with this batch of numbers, and I cannot say anything about anything else. I'm exaggerating a little bit, but that's basically what's going on. So it has a use, not really for us. So like I said, it's a dead end. It's too bad, because it really is so intuitively pleasing. It's so intuitively pleasing, but it just doesn't work. It works for another kind of stats. For non-parametric statistics, it works really well. There must be another way, and clearly there would be, or we'd just stop the course right now. So, and you know there's another way. You know we're going to do standard deviation variance, right? So how else can we get rid of negatives? You square the deviations. Square them. Right, because negative 4 squared is 16, and positive 4 squared is 16. Oh. So I can just square the numbers. The negatives go away. Excellent. You may have heard of the term sum of squares. That's why we're doing this. That's where the term comes from. We're just going to sum some squares. So then I did that. Now I end up with a really big number because I've squared this thing. So that means that must be a squared quantity. So it's negative 12 squared, that's 144, 64, 16, 49, 289. Add them up. funny, that's one of those things that people are always surprised that I know squares of numbers up to like 25 because we were drilled into our heads when I was in school. So, 17 squared is 289. I just know that because we were told that over and over and over again in school, and then you know it. The nice thing is I can usually recognize bad numbers, and it's harder for all you guys because you weren't taught that way. There really was an upside to being told, memorize this. Like, it really helps. It's not fun when you're 12 to memorize tables of numbers, but you know what? You don't forget it. Anyway, by the way, I've been saying this since I was like 30, so this isn't just old man talking. I've been saying this forever. Because I think when I was in school, the last set of people that they made do things like that. I went to very modern schools, by the way, that were very 1970s, and you don't have to come do anything. It was very different, weird time. It's like a holdover from the 60s. I think most of my teachers were on acid. Except for that Mrs. Byers who took my frickin' hockey cards. Anyway, still bitter about that. 112 is a pretty freaking big number, though, for those numbers, right? So it's a squared quantity. We're going to take the square root. Opposite of squaring something is taking the square root. We're going to do that. By the way, this number, the variance can never be negative. It cannot. It is a squared quantity. It must be positive. We are not dealing with imaginary numbers, right? You ever learn about imaginary numbers in school? Right? So square root of -1 is I. So I heard somebody say I. Some of you learned about imaginary numbers. We don't collect imaginary numbers, do we? It's not something we do when we're collecting data. I will say, though, I once had someone, it was a polling thing, they call it, sometimes. If a federal election were held today, how likely would you vote for, and I'm not going to tell you what the party was, but they said, how likely would you vote for this party? If you could put a number on it, from 0 to 100, how likely? So they listed a couple, and then listed another one, and I said, I. And she said, what's I? I said, it's an imaginary number. It's the square root of -1. That's how likely it is I'm going to vote for that party. I actually got a laugh from Polar. I was pretty happy with that. My whole life is just about trying to get laughs. I don't care about anything else. A friend of mine once said, I know your teaching style. You're looking for laughs, and if they learn something, that's fine. Pretty much true. So it's always a positive number. If it ever comes out negative, if you've done it by hand, you've done it wrong. It can't be negative because we don't collect imaginary numbers. By the way, those numbers they're called imaginary, but they're totally useful in like electronics and stuff. So it's not like they're just something somebody invented to go, oh yeah, what's square root of -1 is I. Like it's a real thing that's used in engineering and physics. But who cares about that? Screw those guys. Square root of that's 10.6. Oh, that looks pretty good. It's actually not that different from the mean absolute deviation either. It's, which was like 9.6 or something. That's close. So again, this is intuitively a nice number. This feels right. Right. The problem, my voice went really weird there. I apologize. The problem with this is this formula has an N on the bottom. You know that the issue is here that, well, first of all, I know that also it makes sense to have an N on the bottom. It shouldn't. It's supposed to be N minus 1. What we want is something that is an unbiased estimate of the population. Remember I said before, the beautiful thing about inferential statistics is we can generalize to a population. So we want to be able to do that. So we want to get an unbiased estimator, it's called. If we use N, we get a biased estimator. So if we use N, we tend to underpredict the value of the variance in the population, the standard deviation of the population. If we divide by N minus 1, we actually get an accurate prediction. Now, for the population, if you were to calculate this value, it actually is n log. But for the standard deviation, for the sample statistic used to estimate it, it's n minus 1. Okay? So the denominator is n minus 1 when it's a sample statistic. And unless it's pretty clear that it's a sample, a population, always assume we're dealing with a sample. Always assume we're dealing with a sample. On the other hand, if I said, am I significantly taller than Skylar? That's a stupid question. I just am taller. With a tape measure, I'm taller. Done. Next question. There's no stats you have to do. Because that's a population. There's a me and a him. We're done. The population of me, a population of you, and that's it. Yes? Okay. However, if we're comparing two groups that are clearly not populations, obviously at that point we're using a sample statistic. So it underestimates, if you don't have that in the bottom, it underestimates the population parameters. But the nice thing is we know by exactly how much, and if we subtract 1 from the denominator, I still have to think if I have numerator, denominator every single time. Whenever I say numerator, denominator, watch me, I pause because I go numerator, denominator to myself. It's like the thing with the alligator mouth. What are we doing here? 11:15. Do I want to do one more slide? Yeah, I'll do one more slide. Because the slide is this. So here are the formulas for standard deviation and variance in the sample. And that's all we really usually do. All we really care about populations, but we can't study populations. So we take samples and generalize the populations. So you guys probably all know these two formulas. You've seen them before. Okay. All right. So how do you know how much? So like how do you know how much to take off the denominator? I just did it again. Like to go all watch. I always look up. It's like I'm thinking. How do you know how many numbers to take off? Well, with the variance standard deviation, it's always n minus 1. There's other cases where, as we go along, it's not going to be n minus 1. Not for these, but for other things, when we're doing what are called degrees of freedom. It's based on how many things you have fixed. In this case, we fixed one value. We said the mean has to be this. There is a constraint on the numbers. The numbers cannot vary completely freely. They can vary, but they must, in this case, sum to, what's the total again? Whatever it is. Can't remember. 65. They must sum to 65. Because that's already there in the formula. So we've lost one of these degrees of freedom. By the way, this leads to one of the few statistics jokes. There aren't very many. These two unbiased estimators are talking in a bar. And one says to the other, how do you like being married? And he says, it's okay as long as you don't mind losing a degree of freedom. That's the closest thing to a joke in statistics. There's not a lot. As my stats prof used to say back in grad school, this field is for people who find that being an accountant a little too edgy. That's kind of what it is. All right, any questions? Because we can pack it up for today, so we can do one Thursday. Good? All right, everybody, thanks. See you then. Oh my God. Where the fuck is my... Okay, so this is where right here is where we left off. We had the equation or formula, whatever you want to call it, for standard deviation. Right? No worries. So we have the formula for standard deviation and went through this, right? So we had our batch of numbers, which was what? 1, 5, 9, 20, and 30, and what we're doing here is we're doing a standard deviation of those. And for that batch of numbers, we got 11.85. right? And if you remember, the other one was what? It was 9 or 10 point something. So we have a number, we have a thing, a quantity we can assign to describe spread. And it's in the same units as the thing itself. So the only issue with variance, and in fact you'll find as we go through the course that we usually use variance. We don't use standard deviation. But, you know, one's 1 squared, and the other 1 squared root. It's no big deal. Oddly, we use variance more than we use standard deviation, but standard deviation, at least for descriptive purposes, is the same units. And variance is in squared units, right? So that's why, because that's the nice thing about this, we actually now have a number, and we can compare a couple of numbers. Now, can you actually statistically compare standard deviations and do a statistical test? Yeah, sure. Sure. In fact, though, you know what you do? You compare variances. Everything's done with variances behind the scenes. Though this helps us in as I said, in descriptive purposes. Right? So remember that was 11.885, and we had another number. Let's go back. Did we get another number? Oh no. Maybe I did. Did I work that out? As I go back and forth through the freaking thing. No, I guess I did not show that. Okay. Good. Well, this is all stuff we've done. Great, and that was the sample statistics. Remember different population parameters. Okay, so that's our sample statistic. And we talked the other day about how the denominator has to be n minus 1 and not n. And it's a strange deal that this happens. But it happens because of math. If you used n, which intuitively is much more pleasing, if you used n, you would be underestimating the size, is that right? Does it be a smaller, so bigger number, smaller number, yes. Underestimating the standard deviation variance. The cool thing is we know exactly by how much. That's the wild part of it. So if we didn't know exactly how much, it wouldn't matter. We would be screwed. But we know by exactly how much. And if it's n minus 1. It's 1 minus, like it's the number of subjects, number of observations, whatever, minus 1. The 1 happens because we have fixed one value. I'm not going to get into why, because it takes a lot of more calculus than I'm comfortable teaching. But I can tell you that whenever you fix a value, you lose something, and the thing you lose, as you all know, is a degree of freedom, right? We talked about the other day. So the cool thing is we know by how much we underestimate the sample the population parameter. We know we do that by the degrees of freedom. It's beautiful. Okay. So just n minus 1. And the thing we have fixed is the mean. And you might think to yourself, what? What do you mean we fixed the mean? Okay, remember, the numbers don't know where they come from. The numbers have no knowledge at all. They are just numbers. So that x bar may not know. It doesn't know that it's been calculated. You know that you calculate it. If you calculate it, because you calculate it from the sample, right? Remember, it's 13. That's put a restriction on the numbers. Some freedom is gone from the numbers. And you can do this over and over and over again, but if we were to make up 5 numbers that have the mean of 13, they must sum to 65. That's just arithmetic. There's no other way they can work. So we can assign 4 of those numbers arbitrarily, like 6 and 8 and minus 2 and 21, 14, 13, 12, 33, right? That adds up to 33. So what we have left here, to make that to 65, we're going to have to do what? The number has to be 32. There's no other number it can be. It must be. Now you're saying, but Dave, these numbers didn't vary on their own. I know, they don't know that. Numbers don't know things. The numbers don't know where they came from. But you know where they came from. And you know that to satisfy this, to make this true, to then do this calculation, this must add up to 65, which means this must be 32. Right? It must be 65. It cannot not be 65. Because the mean is 13 and there's 5 observations. There's nothing else it could be. And there will be times in the course as we go along where we'll say, what are the degrees of freedom? And you'll say 1, and I'll say, no, it's not n minus 1. It's not always n minus 1. Sometimes we've set 2. We fixed 2 we fixed 2 values in a calculation. If we fix 2, we lose 2 degrees of freedom. Okay. So like I said, you got to remember, numbers don't know where they came from. Means don't. Means of means. We'll talk about means of means a lot, and variances of variances. Okay, what do you mean you can do a mean of a? What about a variance of a bunch of means? We'll do that too. It's the central limit theorem. It's all that. The numbers don't know that they were numbers that came from somewhere else. It doesn't matter. It's an important thing to remember. So my stats prof in grad school, Dr. Spence, Ian Spence, used to always say that. The numbers don't know where they come from, Brockneck. He's Scottish. He wrote me a letter of recommendation for my job. And I got it, so I guess it was a good letter. So for the population, however, it is the big N. The population, this is a population parameter. These are characteristics, these are numbers, a parameter is a number that describes a population. It is a characteristic of a population. Just like Chloe has blonde hair. It just is. We didn't calculate anything. We could, I don't know how we calculate that. In this case, you could calculate it, but it actually is just a characteristic. It's an inherent property of a population. Okay? It's calculable, but it is a property of a population. Population parameter, sample, statistic. They are conveniently both alliterations. Don't mix them up. Sample statistics are there to estimate population parameters. We don't care about samples, even though we work with them. We care about populations. So we're generalizing the population. The thing is, while we don't care about them theoretically, we have to care about samples. Because if we violate assumptions and things like that, everything falls apart. So we don't care about it for our interpretation, but we do care about it to make sure that everything works properly. Okay? So a note also, it's a sigma squared and a sigma. This is a lowercase sigma in Greek, and that's actually an uppercase sigma, the summation sign. The uppercase sigma means summation. The lowercase sigma means variance or standard deviation if it's squared, if you've got variance. Okay? So it is n. It is actually the sum of the squared deviations minus the mean divided by 1. Sorry, divided by n, not divided by 1. Divided by 1, that would be useful. Okay. Questions at this point? Are you getting all that? I mean, I think this is all stuff you've probably seen before and you probably know it's kind of reviewy, but I want to make sure that you're good, because I'll keep going if you're good. Okay, how are the variance and standard deviation affected by extreme scores? This is extreme. This is, just like saying that sometimes it's Harold and Kumar thing that I remember. Anyway, we have numbers to describe numbers. That's what statistics and parameters are. We use them all the time, right? You know about this, your academic average. Right, you take a look and you do your student summary thing in the student portal and you look and it says what your average is at the bottom. Right? It's actually a weighted average because it's weighted by the number of credits the course is worth, which are almost always 3, so it doesn't matter. And also, weirdly, anything you fail, we don't count in your academic average, and I don't know why. I find it very strange. But that's fine, whatever. But you could calculate it. I know a lot of you know it. I always do my average. Right? Always knew it. I even wrote a little computer program trying to determine how much I'd need all my assignments up at that point to get an A. I was one of those kids. So there's a batch of numbers, 1, 5, 9, 20, 30. The standard deviation, that's 11.85. Right, we did that before. So let's throw another number, I don't know, 729. 27 squared, 729. Let's put that in there, let's see what happens. Well, now we have 1, 5, 9, 20, 30, and 729. Our new mean is 132, and before it was 13. So one number really pulled the mean up. But what's it do, as we would expect, obviously, but what does it do to the standard deviation? Our new variance is 85,000, and our new standard deviation is 292.5. I just trust that I did the calculations properly. If I didn't, it's still something like that. If I made a mistake on the mechanical error, which I very well might have. The point is, that's a lot bigger than we had before. Like way bigger, right? So one extreme score, that's only 6 scores all told, so maybe you'd expect that. Right? The mean is affected by extreme scores, obviously, so therefore the standard deviation is. Take a look at what's the formula again? Let's throw that formula back up here. Remember, of course, it's the sum of that, right? Well, look, this is right here. The mean is there, and if that is a bigger number, that makes that whole number bigger. Because it's, just look at it, it's a fraction. If the top of the fraction is bigger, the number's bigger. That's one of those properties of the universe. So of course, if you get a bigger mean, it's going to make a bigger standard deviation. A smaller mean will make a smaller standard deviation. It's bound to. Okay? Questions? So as I said the other day, when I was looking at some of my marks from last term, in 2606, I had a larger number than I'd like of people who do very well. And then I looked and I realized they were all people who didn't apparently ever come to class because they did very poorly on everything. Right? So fine. When I took their numbers out, which was about 20 people of the 60 odd in the class, suddenly the standard deviation looked exactly like it should. Because those extreme scores were removed. So this should tell you something, that sometimes you remove extreme scores. Now, I didn't remove them such that, well, I'm removing you from the university, though I thought about it. I don't have that power, sadly. Because if I did, you guys would be fine. We'll take a little walk down the hall. All of you making noise out there, they'd all have to leave. I mean the country. And even if they're from Canada. We would deport all of them to Sweden. It doesn't matter where they're from. I don't know how we will arrange that. Not just out of the city, but out of the whole, just get it. And I mean, like I said, this isn't about where they're from. Local people, they have to leave them. Make noise in the hall, you leave. That seems like a little bit of an extreme position. Fits now with the politics of the times, perhaps. Anyway! Don't think that, obviously. It's affected by extreme scores. My set of marks were affected by extreme scores. So if I remove those from any analysis of the marks, then I was like, okay, fine. I have two separate populations, right? I have people who come to class and people who don't. That's two different populations. And when I looked at the people who come to class, I said, oh, good, everything's fine. When I look through and go, I don't know you, I don't know, I just like look at their names. It's like, I don't know any of these people. It's like, oh, and these people come to class. So it's obvious, right? I have two populations. That'll happen sometimes. It happens a lot. I've talked about this, about how you'll end up with a bimodal distribution a lot of times with statistics classes early on. And with intro classes of anything, first years, all distributions always look like that. Because a lot of people just aren't ready. Just the way it is. There's people who aren't ready, right? Okay. Questions? Okay, very good. Well, let's use this to our advantage. Whoa, that came up slowly? It seems slow. This is something called the coefficient of variation. We're going to try to figure out, like if you've got two batches of numbers and the variances are different, are they different because the means are different, or do we really have different populations? This comes from Katz et al. These are actual real data, 1990. This is discussed in the book, I think. Okay, we have two groups who were given a test. One group studied, one group didn't study. Multiple choice test. And I think, oh God, I can't remember what this was on, what the questions were. They were multiple choice questions, and I think they were physics questions, but I mean, pretty simple physics questions. Stuff you would know how to do in high school. Okay, and some people studied, were told to study, and some people didn't study. And I mean, I think, and again, I think what we have here is people come in the lab, they're given stuff to study for 10 minutes, and then they write the test. So the mean for the study group was much higher than the mean for that. It's not a surprise. I mean, we would expect that. I just said that. We have two different populations. Same thing here. We deport all of these people, even if they're from Canada, right to Sweden. Everybody goes to Sweden. Sweden seems like a nice place. Everybody goes to play hockey. I don't know. I'll stop talking about that. Point is, maybe we have two different populations. Look at the standard deviation differences. This one's really tight. This one's more varied. What? What? Wouldn't you expect there to be less variance? I mean, let's just think about this intuitively. We got two groups of people. They're answering pretty simple physics questions. When I say simple physics questions, I mean like, what's Newton's second law? Like not complicated crap, okay? Stuff you learned in high school. Shouldn't these people be more like, just more variable? I would expect that. Or should they be the same level of variable as these people? Maybe. This is actually saying right now that studying makes your marks more variable, and that seems weird and wrong, doesn't it? Shouldn't it make your marks, like everybody should move up a bunch and either it stays the same, which that would make some sense to me, because it's knowledge, and then, or we would expect more variance, but we got more variance in the study group. Why is that? Okay, well, maybe it's because one has just a bigger mean. Maybe it's just an artifact of how the calculation works over here. So you can conclude there's more variation with study. It would make no sense. However, we have coefficients of variation. This is the CV, or the coefficient of variation, which is just the standard deviation divided by the mean. Oh, okay, we're standardizing it. Now we have a mean, we're going to remove it. Or not remove it, we're going to standardize by that. Because it varies based on that, so divide by that to make it standard. Right? Think about something like drugs. I know that's a very strange segue. But doses are different, having the same effect, have the same effect for different people at different doses because different people weigh different amounts. So we divide by their weight. That's exactly what we're doing here. It's dividing by a weight, and the weight is X bar. And when we do that, they're the same number, basically. So it turns out, in fact, that it's not the case that studying makes it more variable, makes your marks more variable, which would be really weird. Be really weird. This is one of those things, I think I've seen coefficient of variation again once in a paper in my life. It was probably in this. I haven't read this paper. He was a prof. He's a Facebook friend of mine, actually. All right. Okay. Again, we want to learn about samples. Populations, not samples. But the only thing we have to estimate how populations do is samples. All we have are samples. If we knew the population, we wouldn't have to do the experiment. Right? You have to do the experiment for the population. And think about something like an election, which we'll be having one in the next few months probably. Polling is a sample. But election day, when they count all our votes, that's the population. Right? we want unbiased estimators of parameters. Okay? And that's what happens when we have the standard deviation for the sample. It's a biased estimate if we divide by n. It's an unbiased estimate if we divide by n minus 1. An unbiased estimate is still an estimate. But an unbiased estimate is wrong in one direction as much as it's wrong in the other direction. In fact, what that basically says is over over an infinite number of trials, there will be, the error will all cancel, right? So it'll overestimate as much as it underestimates. That's what an unbiased estimator does. It overestimates as much as it underestimates. And again, this is something you'll see soon because we're going to be inundated soon with political polling in the country, right? And we're going to constantly see stuff. It's already ramping up. And day-to-day fluctuations don't mean anything. Really. They can, but it's incredibly rare when day-to-day fluctuations in a poll mean anything. It's mostly just that sometimes you overestimate, sometimes you underestimate. It's incredibly rare when one day some candidate says something and you go, everybody goes, oh, okay, no, now I'm not voting for them. That doesn't happen. It can, but it's very rare. I can think of 2 times in Canadian history. Like in my lifetime, which is most of Canadian, it's not most of Canadian history. So 2 times since I've been voting, I've voted in every federal election, every election I could vote in since 1984. So yeah, twice. It's been a lot of elections. Pretty rare when one thing. So usually you'll say, oh boy, they've made a big deal. No, they haven't. No, it's just fluctuation, just noise. If it happens again the next day and the next day and the next day, you go, okay, something's going on. Something's going on. So we want unbiased estimates of populations, of parameters. So what we have, I'm going to show you, this is an important slide. We're going to go through a lot of example stuff. I know it's the last slide, but you're thinking, we're done? There's a lot more to do. But we're going to do a lot more of this up here. So this is just, first of all, some notation that I want you to learn, which is what the E means. So this is the expected value of. E is expected value. What's an expected value? It's you could maybe say long-term average. You might say the value you would theoretically get if you did an experiment an infinite number of times. This is another way to put it. If you did something an infinite number of times. So the expected value of x is a variable. So let's even back up from what we have here. The expected value of x is x bar. Huh? Okay. Remember, x is a variable. It moves around. So if that's the case, okay, then it can take many different values. Well, what value will it take over time on average? The average! So the expected value of x is x bar. Right? Because the number x, so let's put an actual value to x. Let's not a value to x itself, but what x represents. We're going to say x is heights of human beings. And look, I've got a whole bunch of them right here. Let us pretend that the average height of Algoma University students is 175 centimeters. I don't know that that's true or false, but I made it up. So for any given x, so you're under 175 for sure, you are for sure. So let's take both of them. We're randomly selecting people we get. No, it's not x bar, it's not 175, you're shorter. And then we find out, let's see, a couple taller people back here, me as well, you as well. We're taller, we're part 175. Oh, that's wrong again. You know what, if we did it a whole bunch of times, I think we'd expect the average, wouldn't we? Like, just think about this intuitively. Don't worry about math for a second. What would we expect? We would expect eventually to get, on average, 175 centimeters. Some will be lower, and some will be higher. I'm not a student. I shouldn't count myself. I'm a student of life. I love when people say crap like that. I went to the school of hard knocks. Really? What's the tuition there? I don't know why things bother me. You guys know that the closest thing I have to therapy is lecturing. Anyway, so I did therapy. I mean, you know, psychologist, so you have trouble, you go. It's kind of fun. Guy says, "What do you do for a living?" I said, "Psychologist." He looks at me and says, "No, not that kind. I know about bird memory." He's like, "Oh, okay. I'm not sure I knew that was a thing." The best part was he said, "You seem to just take all my advice." I said, "You don't have to convince me this works. You're one of us. It's okay. Just tell me what to do, Doc, and I'll do it, man." He's like, "Act happy." I said, "Oh, because cognition follows behavior. I taught that this morning." He's like, "I usually have to convince people that after like 5 sessions." I said, "No, that's fine. I'll do that. I'll just start smiling." That's when I felt better. It's the weirdest thing. Anyway, I don't know how I got there. I'm sorry. I think I mentioned therapy. That's where it was. The expected value of a number is its average. The individual numbers may not be. Right? Does that make sense? Does everybody follow that? That the expected value, everybody's good. I can't see, remember that. Okay, but I vaguely see some smiles. They could be the smile of just complete vacancy. It's like, I have no idea what's going on, but I don't want to admit it. That's me in graduate school, all the way through for the first 2 weeks of PhD stats. Yeah, sure, I'm following this perfectly. Look over at my buddy beside me. Did you do this in high school? Matrix algebra. Yeah, photocopies like a 4th year math book for prospects. You should all learn this. Okay. Anyway, so if we took a number and added it, k, a constant. Now k doesn't vary; it's a constant. Okay. So remember, we said our hypothetical average height of Algoma University students is 175 centimeters. And then we're just going to, for some reason, add 10 to all of them. Now, what number would we expect? X bar, 175, plus the constant, plus 10 more. So then we would expect 185. Okay. If the average in a class, let's say that on the first quiz, the quizzes are at 10, right? Let's say the first quiz, the average is, I don't know. Okay, I'm just making up a number so there's room for me to play with this. Please don't go, "Oh no!" Let's say the average is 4 out of 10 in the first quiz. Could be. Probably won't be that long. If it is, you don't worry, it's a quiz. Anyway, so we wouldn't know what everybody got on the quiz by just knowing the 4, right? So if I just said, I'm just picking one, I got Carter's quiz here. Is it 4? We don't know it's going to be 4, but we know if we put everybody's quiz together, the average is 4. Those are the X's. Now, I say to all you guys, well, you know, I'm known as, if I'm known for anything in my teaching, it's that I'm a pushover and I give in to students all the time. Sorry, I couldn't say that without laughing. I'm going to give you guys all 2 points. Now you all get, now the average is 6. So I just did, I just added a constant. So we don't know that, let's say Carter actually got 10. Now Carter gets 12 out of 10. Well done, buddy. The Skylar only got 3. Sorry, buddy. Now you got 5. Right? Individuals all go up by the same amount. That means the average goes up by the same amount. The expected value of x plus k is x bar plus k. Does that make sense? Good. Okay. Now here's another notation. Var. The variance of x is the variance. That's okay. That's is just going to be s squared sub x. But the variance of x. So again, let's go with the quiz marks rather than the heights. So I get all your quiz marks, and let's say the average, the standard deviation rather was 4. That seems too high. Let's make it 2, because the average is 4. Let's go with 2. That's still even a little high, but fine. and I add 2 to everybody's points. Does that change the standard deviation? Well, no. You went from 7 to 9, and you went from, what do you want to get?
I don't know, like a 7.
7 to 9 again. 6 to 8, 10 to 12. Nailed it. You only got 3, right? 3 to 5. You kind of totally blew it, Skylar. And I'm sorry. Study! Okay, so this afternoon, I said, don't study too much for the quiz. That's the joke. Okay. Did you see what happened? We moved the average up. But did we spread the marks out at all anymore? No. Because look, here's the distribution. I am the distribution. I'm going to move over. Doesn't matter where I go, I'm adding the same amount all the time. I'm going to stop doing that now. Hurt my shoulder the other day shoveling a driveway, and it's still a little bad. Yeah, I'm sitting. My brother was in a head-on collision yesterday, but I hurt my shoulder shoveling, so I said to him, yeah, we had a rough day, eh? You had that? I left my iPad in the classroom for 3 hours. So for both of us, it was pretty intense, I guess, eh? By the way, he's fine. He's home. He said he's still picking glass out of his hair. Wear your seatbelt, eh? Because if he wasn't wearing a seatbelt, he would have gone through the sunroof of his car. And I'd have a dead brother. And now I just have one I can make fun of for, I'm going to make fun of a little later. We're not quite there yet. Doing that to the variance did nothing. It's the same. It's the same. That follows, right? Makes sense. Okay, so if you add or subtract from the variance, and remember, subtracting is just adding. It's adding a negative number. You get it in your head. So if we subtract or if we add, it doesn't do anything to the variance at all. Now, what if, again, let's use the quiz example, we're going to multiply your scores by something. And this is, in fact, on the odd time, and I have done it in the past. There are times when it's completely on me that a test is too hard. It happens. It happens. Usually it's because I thought I taught something more than I did. And I go back and listen to the podcast and go, oh, I told them not to worry about that. And that was the essay question. That hasn't happened. But sometimes there's a couple of definitions and it's like, oh, okay. I think what I'll do is I will correct that. But I don't correct things by adding a constant, because that I don't think is fair. I don't think it's fair to people who did really well. If you get 10 out of 10, you get 10 out of 12 on the 10 out of 10 on the quiz. No, it's Carter. Let's say you get 2. Add 2 to yours. I've added what, 20% to yours, but remember Skylar only got 3. I'm sorry, dude. Later on, we'll make fun of somebody else.
This is what I get for messing up the first midterm last semester.
So he had 3. We added 2. Well, that I've given him 67% more points, and I've given you 20% more. That doesn't seem fair. What I like to do is I multiply times a constant. So everybody who goes 20% higher. So 1.2, something like that. And of course, all that does is just make the expected value of x times k is x bar times k. So x bar was, what was it, 4, I said? Now it's, and I multiply times 1.2. 4 times 1.2 is 4.8. I think I did that right in my head. Yeah. So the average has gone up to a point where I'm happy with it, and it's helped you guys, percentage, as much as it's helped all of you guys. So I find that fairer. That's how if I ever do adjust grades, which I don't do very often, but I have. The one time I did it, this is the perils of using a test bank. So behind the fourth wall, we get stuff from textbook companies. I don't use any of it, but that's not saying I'm better than other people. Well, it kind of is. But they also give you, and especially for something like intro psych, like I'm not an expert in anything except like 2 chapters of intro, right? The whole thing. So there's times when I'm teaching social psychology, thinking to myself, I didn't even take a social psych class. No idea. And I'm going, well, the fundamental attribution error, by the way, that's the only social psych I know. So I would use a test bank, and it came with software, and you could say, how hard do you want the questions? And it's like, I'd like them moderately hard, and a few really hard ones, and a few really, like you can do all this stuff. Click, 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 click. Gives me a test. I go to, this is a long time ago, obviously. I take it to my secretary to type, amazing, right? Different time. Right, 25 years ago. I mean, I think our secretary is much less. There, Sheila, can you print this out? So type this, print this, she does, no problem. She gives me 100 quizzes, 100 exams. I hand them out to the intro psych class. I get the back average is like 40%. I'm like, what happened? What did I, because that was clearly on me. What did I do? It shouldn't be that low. I look, and the textbook company sent me the question bank for the wrong textbook. An intro psych book, just not the one I was using. So it covered things at different times. So had it been for a final exam, it would have been fine. But it wasn't for a final exam. So I multiplied everybody's score by a constant. I said, okay, the first midterm, or the first test in intro psych, typically what you get is around a 62 average. And I just figured out, okay, 62 divided by 40. And okay, I'm going to go up by that much, so about 1.5. Do it. Done. That's the one time, that was a real screw up. And that's one of the reasons I don't use test banks anymore. It's like, uh-oh. I mean, of course, what do I say? Well, I'm blind, I couldn't see it. I never said that. I wouldn't say that, I didn't say it, I wouldn't do that. I would never use my disability as an excuse unless it's to get seats at a hockey game. Or a baseball game. Remember my dad, we were at a Montreal Expos game years ago. Obviously the Expos haven't existed since 2005. And we're at a game, and I guess it was probably in the early 1980s, and it's an afternoon game. So there's not a lot of people at the stadium. And there's maybe 20, 15,000, 18,000 people. There's a lot of empty seats. And my dad, we keep seeing people going from our cheap seats, where we were, down to these good seats, which are season tickets. But they get caught, and the ushers keep telling them to go back. So my dad goes up to an usher, and he says, my kid's like blind, right? You hardly see the game. Can we go sit down there? I was like, yeah, sure, go there. So I once, when my son's at Xbox 360, Red Ring of Death, remember that thing? Didn't work. This was maybe 18 years ago, 15 years ago, around then. Yeah, something like that. And I found out, I called I shipped it off, I called Microsoft. Of course, it says call this phone number. And they said, we'll send you a shipping label, we'll email it to you. And I said, is there any way you can expedite this repair? My son's autistic. It has nothing to do with anything. And the guy's like, oh, totally. You know what we'll do? We'll send you a brand new one. And we'll just, I said, okay. And it's like, hey, John, anything else you can break? You want to bust anything? I'm not above using it. If you're disabled, you get screwed around enough, so now and then, game the system. That's what I'm saying.
Yeah.
Yeah. See, you know.
I know.
You know. Now the bonus points come in. Now he's up to 10 out of 10. Okay. So what happens to the standard deviation, or to the expected value, goes up x bar times k. What happens to the variance? This is always the hardest one, I think, to get your head around. Now think about individual scores. They're being changed by a constant. They're being multiplied. So some scores go up more than others. Because like 10 times 1.2 is 12, and 1 times 1.2 is 1.2. So one went up by 2, one goes up by 0.2. That's going to change the variance. But we know how much we multiplied by. And variance is a squared quantity. So it's s squared sub x times k squared. So if I'm going to multiply, let's pretend that in my badly given test in Newfoundland, that as much as I can try to blame it on a test bank, it's my fault. Completely and totally my fault. I'm like saying to my friends, what do I do? I can't give them another test. And my friend's like, give them another test, who cares? I'm like, yeah, you're tenured. So multiply everybody's marked, I think it was by 1.4. So we went from 40, it was 1.4, I'm almost certain what it was, something like that, or 1.5. So 1.5. Would have been 1.5 actually, yeah, 1.5. So now the average went from 40 to 60. Let's say the variance was 10. It's a reasonable variance. Just a little high. Variance, a little low rather. Variance is 10, and we multiply, what did I say, by 1.4? So that's, is it 1.69? Is that what 114 squared is? Nobody has a calculator? 1.4 times 1.4. Yeah, 1.96. 1.69. I transpose the digits in my head. So we multiply our 1.69 or 1.96, where it was 1.96, yeah, times 10. So now it's 19.6 our variance, because we multiply that times the square of our constant, because it's a squared quantity. So that means the standard deviation is going to be just s times k, because it's the square root of this. Okay? That's the square root of it. If that's the square root, just take the square root of that quantity. So if I multiply all the values times 2, the variance goes up by a factor of 4. But the standard deviation goes up by a factor of 2, because it's not a squared quantity. Questions so far? Are you actually internalizing this? Okay, I think you are. I think you are. Because I'm going to ask you a question like this on the quiz. That's why I'm asking if you get it. I don't want you to get 4. I don't want an average of 4. Better than 3 is all I'm asking. Done? Okay, good job. Because I'm going to give you some numbers. So instead of working with x's and k's, I'm going to give you some numbers. And I'm going to ask you to work with them a little bit. You'll be able to use a calculator, and I shuddered. I usually make it so you should be able to do it in your head, but fine, use a calculator. Can't you do arithmetic in your head? But why not? People are always amazed. You go to the corner store, and they know how much tax is. It's like, how'd you do that? I said, I multiplied times 13 in my head. I'm sorry, is that difficult? Anyway. Here's a calculator right here. I didn't even bring it. There's calculators just in nature. They're just sitting around. It's just like wild calculators. We used to play this game when I was an undergrad. We called it openers in nature. Anything can be a beer opener if you think about it hard enough. Right? So, we called it openers in nature. Anyway, it wasn't really a game so much as a thing we said. Right. Okay. Next slide. So, and this is actually the last slide. But I want to maybe go over some stuff after. We'll see how it goes. EDA is actually incredibly easy to do. And if you've played with SPSS at all, and a couple of you have already handed in your assignments, which is great, but go play with SPSS and just click on descriptives. So put a bunch of numbers in, and there is a batch of numbers you could use that are on the assignment. So you're already playing with it. Just click on descriptives. You get tons of stuff. You get things like kurtosis and skewness, like numbers for them that, again, I don't know how to interpret. But you get them. And it's overlooked constantly, and it drives me batty. It's funny because it happens that this is the place to find out there's problems. Right? Like if you had a graph that looked like this, and we look at the error bars like that. Oh, I shouldn't have done that. Anyway, I didn't do it. Skylar did it. You saw that. If that happened, you go, there's a difference. Like, if you saw that in your exploratory data analysis, you go, oh, look at that, I win. And then you did the analysis and you went, oh, but of course, these error bars overlap. Maybe I lost. It shouldn't be like that shouldn't happen. That should be a difference. Right? Like, it's there, but the statistics are telling us that it's not a significant difference. But we can see the difference right there. So what's the problem? It may be that it's not a significant difference. It may very well be that there's nothing you can do, and that's just noise. Like I said, some days, you'll see this again shortly when all the political polls start up big time. Some days there's just a weird poll. This is the same kind of thing. This just could be a weird sample. But what if theoretically this all completely fits, this group being higher than this group? What if that actually fits perfectly with your and other people's theoretical notions, right, of how things are supposed to work? So you lay everything up in your introduction and all this stuff, and this is why I'm doing this experiment. I'm going to do it this way, and it should look like that. And then you find the difference, and you say it's not significant. You're like, yeah, but 200 other papers tell me it's supposed to look like that. Either I'm blowing the lid off something, or there's a problem here. And the problem, obviously, is the variance, right? One's way bigger than another. So what we end up doing is a transformation to those data. There are very specific ones you can use in very specific circumstances. So there are ones that are only used for percentages, because there are certain problems that percentages have. There are ones that are only used for counts, for like frequencies, because there are certain properties counts of numbers have, or counts of objects have. We'll talk about that later on in the course, but the reason I want to talk about this, as I said now, is I want to just lay the groundwork for the idea that if we do something to a set of numbers, the numbers are the same. The numbers don't know what you did to them. And there's nothing wrong with doing that as long as you know what you did. All you're doing here is changing the scale when you do transformations. Celsius and Fahrenheit. Right? You listen to the radio. If you ever listen to the radio from across the river, who listens to the radio? Nobody listens to the radio. But sometimes listen to Greyhound games and on the radio. And then weirdly, the radio channel that has the rights to broadcast Greyhound games in Canada is from the States. So they always do their weather in Fahrenheit. But it's still the same. Like when they say, yes, and the high today will be 42, you go, oh, it's going to be hot over there in the States. No, it's 42 Fahrenheit. Right? It's a totally valid measure of temperature. It's just not one we use here or anywhere else except Liberia and Myanmar. Inches, feet, football fields, eagles. You ever notice that? You see things from the States, they always measure things in football fields. That's like 8 football fields. It's like, how many square meters is it? Oh, it's like 8 football fields. It's like I said, do exploratory data analysis. It's easy to do. You do it, you spot things like this, and you fix them. And you fix them with transformations. Not always, sometimes that's just the property of things. But I've had students more than once, more than 5 times, who've done their thesis with me, come and they've analyzed their data and they bring me all their stuff and say nothing happened. And I look and I say, yeah, but, and again, exploratory data analysis, they'll have all that. And I say, yeah, but look, what's going on here? Oh yeah, it's not significant. This is an old student of mine, Shauna Barrett, PhD, Dr. Barrett, and she had collected really cool data on swearing. It's fascinating stuff. And she didn't find a significant difference. And it looked like that. And we're like, yeah, but, and I said, you're counting how many times people have noticed that people are swearing? And she said, yes. I said, oh, I know what the problem is. I said, multiply all your numbers by 2 times the arcsine square root of the values. And she looked at me and I said, you didn't pay attention in 3256, did you? I haven't taught you that yet, don't worry. It's not that you haven't paid attention. And of course, what Shauna said at that time, because that's how she always talks to me, is, I fucking hate you. And then she starts emails that way. I still now and then get communication from her. It's like, shut up, I fucking hate you. How are you? Right. When she said, I want to do my honors thesis on the basis of swearing, I looked at her and I said, really, that's a real surprise coming from you. Like, she swears more than I do. And she lives in like that's all corporate stuff now. I don't know how she gets through the day. Probably by swearing a lot under her breath. But once I did that, then it's like, oh, look, it worked. It kind of worked. Her thesis didn't work perfectly. But it was nice. Right, so do this, and then it can save you a lot of pain. Now, I'm done what I want to do for today. We're exactly where I want to be. But I want to know if you have any questions because I can answer them. If not, we're finished. We're fine for today. I don't want to do too much of this. I'm not going to try to kill you. It's not fair. All right, I'll see you next time. And I don't know, go home.
I wish.
Oh, I see it.